Hello everyone, today I'm presenting our work, CSD-VAR, Content Style Decomposition in Visual Autoregressive Models. This task can be seen as a dual personalization problem. From a single image, we want to extract two things: the content, meaning the structure and details, and the style, meaning the color and artistic technique. By separating these two, we unlock powerful applications. Recontextualization, where the same subject can be placed into entirely new scenes, and style transfer, where the extracted style can be applied to brand new content. But current state-of-the-art methods struggle. They suffer from content, style, and prompt misalignment. And often there's content leakage. Style representation accidentally contains subject information. So, current solutions like B-LoRa or Inspiration Tree don't fully achieve clean separation of content and style. Our motivation comes from the generation process of Visual Autoregressive Models, or VAR. Instead of generating pixels all at once, it works scale by scale, from tiny token maps at low resolution to finer details at high resolution. Therefore, this multi-scale process naturally raises the question: can different scales specialize in content versus style? To answer that, we collect 35 images covering diverse styles. Then we ran a three-step scale analysis. First, we extract token maps at all scales for each image. Secondly, remove the tokens at a target scale and reconstruct the image. Finally, we measure the style similarity between the reconstruction and the original. This reveals which scales are most style-sensitive. The earliest scales, and even the final scale, encode style most strongly. Therefore, this scale separation is the key insight that drives our method. With that scale insight in mind, let's briefly revisit how VAR is trained in our baseline. We use cross-entropy at every scale with a teacher-forcing training scheme, meaning, instead of conditioning on the model's own previous predictions, we feed the ground truth token maps from earlier scales into the next. This stabilizes learning and lets us parallelize across scales. During training, the pre-trained VAR backbone is frozen, while our text embeddings are learnable, so gradient flow is routed into those embeddings. This gives an optimization baseline, but on its own, it doesn't disentangle content and style, which sets up our three improvements next. So we propose CSD-VAR. The first component is our scale-aware alternating optimization strategy. We design separate losses, loss content and loss style, and optimize them at their corresponding scales. For content update iteration, we compute loss content on the all scales except the early ones, and the gradient flows only into content embedding, while style embedding and the VAR backbone stay frozen. Next style update iteration, we compute loss style on the early, and with a small alpha tap on the last scale, and the gradient flows only into style embedding. By alternating updates, we prevent gradient mixing and achieve clearer separation of content and style. Even though the last scale can help style embeddings capture fine style attribute, it also risks content leakage into style. Therefore, we tackle this problem with our proposed SVD-based style embedding rectification. The idea is to remove content-related directions from the style embedding. Particularly, first, encode the prompt and take the style token output from the text encoder as the style embedding ES. Next, build a content subspace for the concept, such as cat. Gather generic subconcepts, variants, encode them with clip to form a matrix M, run SVD open parenthesis M equals USIGM ATVT close parenthesis, and take the top R right singular vectors VR to form the projection matrix P project. Now remove the content component from ES by subtracting its projection onto that subspace. This keeps directions tied to style while zeroing content leakage. For a comparison, dog in ES style shows leaked cat traits, while dog in ES style shows pure style, no subject leakage. Now, with the two above improvements, content and style are much better separated. But what about complex concepts? Sometimes textual embeddings alone are insufficient. That's why we introduced the third component: augmented key-value memories. These augmented KV memories act as extra storage in the transformer. We insert them at specific scales: style at the first scale and content at the fourth scale. This allows the model to preserve subject identity more faithfully, beyond what text embeddings alone can capture. Of course, we also needed a way to evaluate this task, so we built CSD-100, a dataset of 100 images designed specifically for content-style decomposition. It covers diverse content categories and style categories, enabling robust benchmarking of this new task. Our experiments use the CSD-100 dataset, with 25 prompts for content and 25 prompts for style. We evaluate with 3 groups of metrics: 1. Content alignment; 2. Style alignment; 3. Text alignment. Higher scores mean better disentanglement and alignment. Here are the quantitative results on the CSD-100 benchmark. Across all metrics, CSD-VAR outperforms prior methods. This shows our method achieves both stronger content preservation and faithful stylization. Moreover, CSD-VAR is backbone agnostic. The same approach works with text-to-image VAR backbones, including SWITI and Infinity. And qualitatively, the difference is clear. CSD-VAR generates results that both stay true to the content and follow the style. Other methods either overfit to style or fail to preserve the subject. Our method produces the cleanest decomposition in practice. To conclude, we introduced CSD-VAR, the first approach to content-style decomposition in VAR, along with the CSD-100 dataset. Our contributions are: 1. Scale-aware optimization for better separation; 2. Rectification to prevent leakage; 3. Augmented KV for stronger identity preservation. Thank you for listening, and feel free to reach out to me for more details.